Hello, welcome to Basics of Noise and its Measurement. Over this week we have been discussing transmission line equations, and we have also introduced in the last lecture this notion of specific acoustic impedance. So what we are going to do today is discuss another type of one-dimensional tube, and in this particular tube, instead of having a closed end or an open end, which are regarded as perfect terminations, because in one case you have this perfect condition that velocity is 0 for a closed tube, and in the other case you have this perfect condition that pressure is 0, that is for an open tube. You can have a situation where the conditions are not very explicit and so clear, and rather at one end of the tube you know the impedance of the system. So if you know that there is a particular material which is being used to close the tube, that may not necessarily translate into a perfectly closed end or a perfectly open end, because to have a perfectly closed end you need a perfectly rigid closure, which is not the case in real systems, and so it's a imperfect termination. So those are the tubes which we are going to discuss, and we will see how we can address those tubes and what we can make out of such type of tubes. So what we are going to discuss is tubes with imperfect terminations. So what does this mean? Suppose you have some tube of length L, and at this end of the tube I am using some material, okay, and this is not a perfectly rigid material, so it can absorb a part of the sound, and it also bends because of the pressure of the sound pressure, because of sound pressure inside the tube. So things are not as explicit as we saw in case of closed and open tubes, or even for the case of semi-infinite tubes. So all what we know is based on some measurement, and we will discuss how we measure these things, but we have figured out that the impedance, specific acoustic impedance, is ZL. So what is known is that at x is equal to 0, Z, that is specific acoustic impedance, equals some value ZL. How we will measure this ZL, we will discuss it in the next lecture, but at least today we will introduce this notion of imperfect termination, and we want to see what kind of mathematical relations govern this tube. So once again, this end is being excited by a piston, and this is x is equal to 0, this is x is equal to minus L, this is my positive x, okay. The sound is traveling like this. So what we do is, again, we start with our transmission line equations. And this is equal to real of P plus P minus P plus over Z naught minus P minus over Z naught E minus j omega x over C E j omega x over C E j omega t So again, once again, these are the general TL equations, transmission line equations. Now Let us see what we have at x is equal to 0. So, at x is equal to 0, we will write the same equations. At x is equal to 0, p of x and t is equal to p of 0 and t, and what I do is I put the value of x in this vector e minus j omega x over c and e j omega x over c. So, what I get is real of p plus p minus, because e minus j omega x over c is 0 is 1 at x equals 0, and same thing is true for e j omega x over c at x equals 0, e j omega t. And similarly, velocity is equal to at origin u0. So, I am going to erase these to eliminate confusion. At x is equal to 0, u of 0 of t is equal to real of p plus minus p minus e j omega t. Okay. And of course, I have to multiply it by 1 over z naught. So, this is the expression for the actual pressure P, and this is the expression for actual velocity u. But the term in this parenthesis is complex pressure and complex velocity. So, if I remove this parameter real or function real, then what the left hand side is no longer complex real pressure or real velocity, but rather it is complex pressure. So, I will express it as capital P, it is complex pressure, and again this is complex velocity. So, I will express it in capital letters. So, these are the expressions for complex pressure and velocity at x is equal to 0. And again these are valid for all situations, because right now we have not introduced any boundary condition. We have not introduced any boundary condition. Now we know that specific acoustic impedance is nothing but the ratio of complex pressure and complex velocity. So, if I have to compute the value of a specific acoustic impedance, and this is designated as Z, right. So, if I have to compute the value of this specific acoustic impedance at the origin, then we have already told that the value is given, and it is Z at 0 omega is equal to ZL, and this can change with frequency. So, it is Z omega, and this is nothing but P of 0 and t divided by u of 0 and t. Okay. And if I use these relations, if I use these two relations and put them here, then what I get is P plus P minus divided by P plus minus P minus, right, times Z naught. Okay. So, my ZL, in this case it is known. If I know ZL, then I can express ZL also in terms of P plus and P minus. Now, at this stage I will introduce, so this is my important relation. that the terminal impedance which is known, it influences the complex amplitude P minus and P plus based on this particular relation which we have written here. Now, we know that P minus is the complex amplitude of the wave which is for traveling in the negative direction, and P plus is the amplitude, complex amplitude of the forward traveling wave. So, and when the forward traveling wave hits the end and hits this impedance, it gets reflected. So, I can also express P minus divided by P plus as some number r, and the value of this r, it can change with frequency, because P plus depends on frequency. We had seen originally that P plus and P minus are functions of S, which is the complex frequency. So, but for purposes of brevity, I will just write it as r, but r will always vary, it can always vary with respect to frequency, and this r is known as reflection coefficient. Okay. So, what I can do is I can again use the same expression, that P minus is same as P plus times r, and I can put this back here to get a new relation, and that relation is ZL, and again I am omitting omega just for purposes of brevity. ZL equals Z naught P plus 1 plus r divided by 1 minus r, and P plus is also on the in the denominator. So, I can erase both of these things, and what I am going to do is I am going to erase the whole thing and write a simpler expression, and that is ZL equals Z at the origin equals Z naught 1 plus r divided by 1 minus r. Okay. So, this is the fundamental equation when we have an imperfect termination, and what this tells us is that I can calculate the value of r if I know ZL. If unless I know the conditions at the boundary, I cannot solve the thing. So, if I know the conditions at the boundary, and if the impedance of the material which is used to plug is ZL, then I can use this particular relation ZL equals Z naught times 1 plus r over minus r to compute the value of reflection coefficient. And once I know the reflection coefficient, I know the proportion of P minus and P plus. Once I know the proportion of P minus and P plus, I can use that relationship and use the other boundary condition at the end which is getting excited to compute P plus and P minus. So, this is what I wanted to share in this particular module, and what we have done today is introduced one more parameter and known as reflection coefficient, and we have established a relationship between reflection coefficient and the terminating or terminal impedance in a tube, which is ZL, and the relationship says that ZL equals Z naught, which is the characteristic impedance, times 1 plus r over 1 minus r. Please bear in mind that r as well as ZL can vary with respect to function with respect to frequency. So, if you are handling these parameters, you have to be cognizant of this. So, with this we close this particular lecture, and tomorrow we will continue this discussion, and we will actually learn as to how we can actually measure impedance if we do not know, using some actual instruments. Thank you.